Hello, my name's Mike Wooldridge. I'm a professor of computer science at the University of Oxford, and it's an enormous honour to be invited to present to this first student conference on AI. I think it's a wonderful initiative. I hope we'll see it again in the future, and I just wish that I could be with you today, but if for obvious reasons that isn't possible. So what I'm going to talk about is I'm going to start with a very old story, where I came into the AI field, and that's going to lead me to research that we're doing in the present day, which is to do with understanding equilibrium properties of multi-agent systems. So let's start then with an overview of the talk. And what I'm going to do is I'm going to start by talking about the issue of multi-agent dynamics and why that's important, why we're interested in studying multi-agent dynamics. And then the bulk of the talk is about two approaches to understanding multi-agent dynamics. The first approach based on what's called game theoretic equilibrium analysis, and the second approach based on what's called agent-based modeling. And then that'll lead me to some conclusions and to some future work. So let's kick off then by talking about multi-agent dynamics. Oh dear, I'm only on the third slide and I've already got a typo. That should say dynamics. So there's a very old idea in artificial intelligence which goes back to the 1980s, and it's called the software agent paradigm. And the basic idea of the software agent paradigm is to change the way that we think about software. Most software programs that we interact with, like Microsoft Word or Safari and so on, are essentially dumb and passive tools. They're basically waiting for us to tell them what to do, and we tell them what to do by selecting an item from a menu or clicking on a particular button. But basically the software is just there waiting for us to tell it what to do. And back in the 1980s, a number of researchers, including myself, started to think about changing the paradigm from software being the dumb recipient of our instructions to software that would work with us. Software that would work with us as a proactive, cooperative assistant. And the metaphor that was quite widely used at the time, which still exists in the present day, is that the software acts like a personal assistant, like a human assistant would work with you. So it's not just waiting to be told what to do, it's actively cooperating with you on whatever it is that you're trying to do. So that's the vision of the software agent paradigm. And a lot of people were talking about that vision back in the 1980s, but it took a long time to make agents a reality. And some of the issues that we thought were the important issues at the time turned out not to be important. And some other issues that we didn't realize were important turned out to be very, very important. So the first research on agents took place in the late 80s and early 90s. And by the mid 90s, it was an established research field, but it took 20 years really after that to become after the late 80s to become a reality. But it did become a reality, and we now all carry with us in our pocket an agent, a software agent. So Siri from Apple, Alexa from Amazon, Cortana and Bixby, and all of these other digital assistants, they're all manifestations of that dream. The idea of software as an active, cooperating assistant, something which is working with you on whatever it is that you're trying to do. It's not just waiting to be told what to do. So why did it take so long? Well, I think the Moore's law, good old Moore's law. No plenary talk in AI is a proper plenary talk without mentioning Moore's law. And the truth is that now, the smartphones on which these assistants run are actually incredibly powerful computers. They're basically supercomputers, and we all carry one with us. And that supercomputer is seamlessly connected to the internet. There have been advances in AI. So one of the things that we didn't understand that was going to be quite so central turned out to be very central is voice recognition. And the idea that you give instructions to your smartphone not by typing but by using interacting via the screen, but by speaking to it. And that required competent voice understanding, which in turn required both scientific advances and also lots of compute power. And also, it required the internet, right? The ability to offload a lot of tasks to the internet. And a smartphone agent that couldn't connect to the internet would be rather limited in the things that it could actually do. But there's one important part of the puzzle which didn't really manifest itself in the way that we thought it was going to manifest itself. So when I started my research, I was very clear that where I was aiming was to build multi-agent systems. That is, I expected my Siri to talk to your Siri. And that didn't quite come off the way that we anticipated. We thought that this was going to be, we fully expected that people were going to be carrying around agents in their pockets, but we really thought that those agents would be talking to other agents. And when we talk about multi-agent systems, that's really what we're talking about. Your Siri talking to my Siri, or my Alexa talking to your Siri. About, more generally, it's to do with AI systems that are interacting with each other. That's what multi-agent systems is all about. And I say, it hasn't quite manifested itself in the way that we expected. So a couple of years ago, a large tech company demonstrated a nice demo of software, an agent which could call up a human being, call up, for example, a restaurant, and make a booking on behalf of that human being by talking directly to a human being in the restaurant. But the bit of the puzzle that we expected to be there was that the restaurant itself would have an agent, and my Siri, to make a booking for me, would talk directly to that agent. Now, I believe that this still will happen because it just opens up so many possibilities. It seems to me to be inevitable, just as it seemed inevitable 30 years ago. What I'm not completely clear about is how it's going to be manifested. So, for example, one of the things that we worked on in the early days of multi-agent systems was communication languages which would allow agents to communicate with each other. And that doesn't seem to have, that didn't seem to take off. You know, those languages were developed and standardized, but they didn't seem to take off in any way. But nevertheless, the idea that, you know, AI systems will be the future of AI as AI systems interacting with other AI systems, it's just inevitable, it seems to me. So agents happened. They happened in a big way, but one bit of the puzzle didn't manifest itself in the way that we thought it was going to manifest itself, and that's just the idea of these agents talking to one another. But that's not to say that there aren't multi-agent systems in use today. Indeed, there are. There are many multi-agent systems in use today. So there are multi-agent systems in use in, for example, in security domains, where agent-based techniques are used to compute optimal policies for security agencies. So, for example, that they can give the best defense possible to an airport or a factory or a port of some other kind. But one particularly interesting application is on the global marketplaces, stock markets and currency markets and so on. And this is the idea of high-frequency algorithmic trading. So, most of the trading on the global marketplaces today is actually not done by human beings the way it was 50 years ago. It is done by computer programs, and it's done by computer programs autonomously. And many of those computer programs are driven by AI. They have AI components. And these agents operate on tiny timescales. They're buying and selling things on the order of, milliseconds, or even less than that, probably microseconds. And these timescales are far too small for humans to comprehend or to understand or to take action in. So these programs, these AI programs, these agents are busy going out, buying and selling things completely autonomously with thousands, potentially millions of other agents. That's high-frequency algorithmic trading, and it's absolutely the standard technique that's used in today on the global marketplaces. But there is a ton of evidence that high-frequency algorithmic trading leads to, and systems like that have unpredictable dynamics. So if we go back to 1987, there was a market crash in October 1987, which unfolded over a couple of days. I forget if it was Black Monday or Black Wednesday, but it was one of the most serious crashes in around that time, with quite serious international consequences. Now, as is always the case, there's a big, long, complicated list of reasons for why that happened. But one of them is that the marketplaces in London and the New York Stock Exchange had been computerized. And the idea at the time was not that that computer programs would be doing the buying and selling, but that people very quickly had that idea. But it's just that then the timescales over which the market operated started to compress. That became smaller. And what we're seeing now with high frequency algorithmic trading is that they've been compressed far, far, far beyond that. So the stock market crash in October 87 unfolded over a couple of days. And it was widely reported at the time, and it is believed that one of the causes of that crash is simple feedback loops. So basically what happens is if a stock, for example, becomes distressed and its price starts to go down, if you're holding that stock, you probably want to sell it, right? You've got a risk on your hands, you want to regain liquidity, as they say, so you sell it. But as you sell it, that pushes the price down more. And you get a feedback effect, right? The price going down causes people to sell it, and that pushes the price down even further. You've got a feedback effect. A much more dramatic event, although one which didn't have quite the same global consequences, was in May 2010. And on 6th May 2010, over the afternoon of that day, over a 30-minute period, the Dow Jones Industrial Average lost over $1 trillion. And famously, some very famous shares, including Accenture, briefly traded at a penny a share. However, you would have had to have been very, very quick off the mark to be able to buy shares at that value, because they very quickly rebounced. So the market collapsed and then it rebounded. And within the space of 30 minutes, it had rebounded more or less to where it was. And it then wobbled. And this was a really startling event. If it had stuck at the level that it had collapsed, it would have had huge global consequences. A colleague said, imagine that collapse had taken place at 5 o'clock on a Friday afternoon as the New York Stock Exchange is closed. You would have had, the markets wouldn't reopen for another 2 days. You would have had a disastrous global situation with contagion, as it's called, spreading throughout the world, because so much value has been lost. Other markets would need to respond to that. Investors would need to regain liquidity. They would need to offload stocks that they thought were losing value, and so on. And it would have been a calamity. This is what it looked like. Oh, no, I don't have a picture of what it looked like. So it unfolded over a period of just, as I say, about 30 minutes. A massive collapse followed by a rebound. So to cut a long story short, what my research is about is understanding situations like this. I mean, when I talk about equilibrium properties, as we're going to see, I talk about equilibrium properties in a formal sense, in the formal sense of game theory, but I also talk about equilibrium properties just in the sense of the usual system behaviors. And what I want to try and do is get a handle on the dynamics of multi-agent systems. And the flash crash demonstrates immediately why that's an important thing to do. So I said there were going to be two different approaches that I'm going to talk about, and I'm now going to start to introduce the first one. And this is a very formal approach. It's based on ideas from well-established ideas in computer science, but also ideas in game theory. And I'll explain how those ideas come together. So the basic starting point is that in this approach is that we view the flash crash as a bug. We say, well, this flash crash, this catastrophic market collapse is a bug in the market behavior. And we are well used to, in computer science and AI, we are well used to trying to understand bugs and the causes of bugs. And so why don't we apply all the techniques that we've developed over the years to trying to identify bugs to the problem of identifying these bugs in multi-agent systems? In other words, we treat the flash crash as a bug, we try to find the causes of that bug, and then obviously we want to eliminate them. So let's then talk about some of the ideas which inform approaches to correctness, the correctness problem in computer science. So a basic bit of terminology. Verification is the process of checking that a computer program is correct with respect to its specification. So the idea here is you have some program, think of this as being like the global marketplaces, and then you have some specification, which is a description of the behavior that you want this program to exhibit. And in mentoring computer science, usually this specification is expressed in a formal, precise mathematical language, and we'll see the language that are used. So you've got a program, you've got some property that you want to check of it, and you say, does this program satisfy this specification? And the specification, think of that as being no flash crash. And if the program satisfies the specification, then it doesn't exhibit this property that we're checking. Okay, it exhibits the property that we're checking, that is no flash crash. So a long-term dream in computing is to do verification both formally and in an automated way. That is, formal to give precise mathematical guarantees about program behavior, and automated verification, that is, automation just means we want a computer to check correctness. Now, the most successful approach to this problem is what's called model checking. So this is model checking. It's a technique which was introduced at the very beginning of the 1980s. And in 2007, 3 people won a Turing Award for introducing it. Ed Clark, Alan Emerson and Joseph Sifakis won the Turing Award for this. And the basic idea that they use is as following. The first thing is that the specification, the property that you want to check, like no flash crash, you express that property using the language of temporal logic. What is temporal logic? I'll give you examples in a moment. Basically, it's a language for describing state sequences, And the key point here is that those state sequences are going to correspond to program behaviors. Okay, so we write down the property that we want to check, never a flash crash, using the language of temporal logic. What we then do is we take our program P, and what we do is we abstract from it a model, and we denote that here by MP, which of temporal logic, which represents that program. Okay, so there's a lot packed into what I just said. Basically, the model, M subscript P, is just a directed graph. That's all it is. It's a directed graph in which the states in that graph correspond to program states, and the edges in the graph correspond to the execution of program instructions. So we've got our program text. Think about our program text. What we do is we just take from that, we extract from that in a fairly straightforward way. It can be straightforwardly automated. A directed graph in which the states in that graph correspond to program states and the edges correspond to the execution of program instructions. And what we then do, and this is where it's called model checking, we check that that particular property is true in that particular model. We check that that particular property phi is true in that particular model, M subscript P. And the point is, and this is the notation that's used, right? This just, we read that as M subscript P satisfies, that funny symbol in the middle means satisfies the property phi. And that's the model checking problem. And it turns out model checking can be fairly easily automated. And there are many now industrial strength model checking tools available, which you can download and you can use for model checking. What about the languages? The languages in which we write down our properties, never flash crash, for example. Well, there are many, dozens, if not hundreds, of different temporal logics that have been proposed for this, but 2 stand out as being particularly prominent, and they're called LTL, linear temporal logic, and CTL, computation tree logic. The one that we're going to use mostly is LTL. So here's a picture of model checking then. In the middle, we've got our model checker. This is the program which is going to check for us whether this property holds or not. On the top left, we've got the model. Remember, it's just a directed graph, a state transition graph, in fact, in which the nodes in the graph correspond to states of the program and the edges correspond to the execution of program instructions. Then you've got the specification that you want to check. And this is, don't worry about what this one means, it's just written down in the language of temporal logic. This is the property that you want to check. Think of that as being no flash crash. And what the model checker does is it checks to see whether this particular property holds or doesn't hold. And it will come back and say, yes, the claim is true, or no, it will say it isn't true, and here is why. A useful model checker will give you what are called counterexamples. They'll show you why the property isn't satisfied. So the basic idea is, again, go back to our dream. What we want to do is we want to, on the top left, we want a marketplace. Think of that as the global marketplace. And there on the right, we want no flash crash, and we want to check whether or not the system is going to flash crash or not. Now, I'm going to refine that story in a moment, so hang on to what I just said. Let's have a look at the language of linear temporal logic. It looks a bit eccentric when you first come across it because it's got some slightly funny symbols, but they have a very straightforward meaning. First thing to say is the language extends classical propositional logic. So everything which you get in propositional logic, you get in LTL. So we've got primitive propositions, and throughout this talk I just use big phi to denote primitive propositions. We've got negation and disjunction. And then the usual negation and disjunction, so not and or and implies and if and only if are all there as well. But then we've got these temporal operators. So the circle means in the next state. The diamond means eventually. The box means it is always the case. And this U, these operators are all unary operators. They take a single argument. This one is a binary operator. It takes two arguments. And it says phi remains true until psi becomes true. Okay. In a bit more detail, linear temporal logic, as the name suggests, is a language for talking about state sequences, an individual state sequence. And again, the way that we think about that in computing is that it's a state sequence is just the computation, the sequence of program states that's generated by a program as it executes. Okay, and what we do is we can, when we're asked whether one of these properties is true, what we do is we evaluate it on one of those state sequences. So for example, this formula next phi, if we go to a state sequence and some particular state there, and we're asked to evaluate the formula next phi, we look to see whether phi is satisfied in the next state along on that sequence. So if next phi is true in this state here, if phi is true on the next state of the sequence. The diamond phi, eventually, that's going to be true in this state here if there is some later state on the sequence in which phi is true. The box phi, it's always the case, that's going to be true in this state here if phi is true on all subsequent states on the sequence, including this one. And phi until psi is true on a state sequence if psi is true at some point in the future and phi remains true at all points until we get there. Okay, so let's see some examples now of some properties that you might want to write down using LTL. So diamond not jet lag means eventually I will not have jet lag. Okay, so think of that state sequence. There is some later state on that sequence, some state somewhere down there. We don't care where it is, but some state on which not jet lag is true. So I don't have jet lag. Think of this as being not flash crash, or in this example here, I've written the plane will never crash. Always not crash. These properties like that are called safety properties. This just means that in all the sequences that you get to, we're not in a crash state, so we haven't crashed. But think about, for our example, think about that as there is never a flash crash, right? We can combine these operators. So if we put them together like this, box, diamond, drink beer, what that means is that in all the states that we can get to along this state sequence, in all the states that we can get to, there will subsequently be a state in which I drink beer. So no matter how far down the sequence I go, there will always be a later point at which I drink beer. So what that means is, essentially, I will drink beer infinitely often. So when we want to express the fact that something happens infinitely often, we use this particular combination of temporal operators. Flip those operators around and you get something very different. This says there is eventually a point on this state sequence such that at all subsequent points, you're dead. Right? So what that means is eventually there will come a point at which I'm dead and which I'm dead forever afterwards. And then finally, the until operator. So not friends until you apologize. What that means is on this state sequence, remember, there is subsequently a point on which you apologize, and at all the points until you get there, we are not friends. So not friends is true. So not friends remains true until that point in the future at which you apologize. So we're not friends until you apologize. Okay, now, I've been talking about state sequences, but if you were very alert, you will have noticed that when I showed you my picture of model checking, it wasn't individual states. The system behavior has actually got this, it's a directed graph, and it's got branches in it. Where do those branches come from? They come from either from the program taking input from its environment and deciding what to do based on that input, or there could just be choices the program makes. So the program is just non-deterministic and it has choices that it makes. But how do we evaluate if we've got a query like this, or the drink beer infinitely often or never crash, how do we evaluate that LTL query on a model which looks like this? Well, there are basically two approaches, and they're called reachability and invariance. Okay, so the first is to say, is there some computation of the system on which phi eventually holds? So is there some branch through that tree on which phi holds? Or alternatively, does phi hold on all computations of the system? So we call those two things reachability and invariance. And they're kind of dual properties of each other. And the crucial thing is, well, it all reduces to reachability. Reachability questions on graphs, like the state transition graph representing a program, can be very efficiently automated. They have relatively low complexity, and that ultimately, the efficiency of reachability is the key to making all this work. I'm not going to go into details to the algorithms and so on. Okay, so that's classical model checking, right? And all those tools that I described earlier, Spin and SMV and MCMass and Prism, what they do is they implement basically that classical vision. There's the program, there's the query about the program, yes or no, they come back. Okay, but there are some assumptions built into that view. And one is that there is a single standard of correctness. The specifier is the arbiter of whether this system is correct or not. So the specifier involves some kind of privileged position. But if you go back to the flash crash, or just generally the internet, that seems to be a slightly wonky version of what's going on. It doesn't, because in the flash crash, each of the agents, go back to remember these are computer programs that are trading independently. They're each trying to do the best for themselves, and they're not controlled by anybody, by some third party. It's not the case that there's one individual who controls all of those agents. They're each doing things for their own owner. So how then do we think about correctness in multi-agent systems? Now, one possibility is just we could look at the system and we could just do reachability and invariance checking. With reachability checking, we could say, does this property hold on some path through the system, or does it hold on all paths through the system? Now, that will work, but actually it will miss a big part of the puzzle. Asking does phi hold on some computation of the system doesn't make sense if that computation doesn't correspond to rational choices. That is, there could be bad paths through that state transition graph, but they're never going to be reached because the agents would never choose to do that. They would never make decisions that would lead to that because it wouldn't be in their interest. It would be a stupid thing for them to do. So the way that we think about correctness in multi-agent systems is that we assume that these system components are rational and that they will act rationally in pursuit of their own preferences. Now, under that assumption, not all of the computations can possibly result. Some of them won't result because they don't correspond to rational behaviors by the agents. But checking which properties hold on the rational computations of the system, that is equilibrium checking. That's what we call equilibrium checking. So it's like model checking, but it's checking properties that hold under the assumption that the agents act rationally. And the reason that we call it equilibrium checking is that the model of rational choice that we use is based on equilibrium properties in game theory. So what we do is we adopt a game theoretic standpoint. And what game theoretic standpoint does is it allows us to apply the concept of multi-agent rational choice, and particular game theoretic solution concepts, and the most prominent of those being Nash equilibrium. And that's the one that I'm going to fix on throughout the remainder of this talk. So here then, reachability and invariance are not the key concepts. What we're interested in is whether properties will obtain under the assumption that agents act rationally. And in our model, what that means is that they choose strategies for acting. They make choices that form a Nash equilibrium, which is, as I say, the basic solution concepts. And that gives us two variants of reachability. It gives us variants of reachability and invariance. We could call them Nash reachability and Nash invariance, or E-Nash and A-Nash. And what Nash reachability says is there some rational computation of the system, some computation which could arise through rational actions by the agents in the system, which would result in this property holding in a flash crash, for example. And Nash invariance just says, is it the case that this particular property holds for all combinations of rational choices that our agent could choose? So again, remember what we're doing is we're focusing on the computations of the system which correspond to rational choices by the agents within it. So now we've got our picture. It's changed a little bit. We've still got our model. Now the model's it's still going to be basically a directed graph, but it's going to be a little bit more elaborate. Why is it going to be a little bit more elaborate? It's going to be a bit more elaborate because it's now representing a multi-agent system. And so, for example, those transitions don't just correspond to individual program instructions. They correspond to a tuple of choices, one for each of the agents in the system. But nevertheless, we've got our model, which is described in the same way. We've still got our temporal logic property, never flash crash, that we want to check. But the system also needs to know about our preferences, about the preferences, of the agents in the system that's being modeled. And what the equilibrium checker is going to do is it's going to say, yes, this property is true on some Nash equilibrium, or no, the property is not true on any Nash equilibrium. That's where we're going. And indeed, that's where we get to. So let me introduce the framework that we use for studying this. The first thing to say is we could work with giving our model checker a directed graph representation, which is what we've done there. But directed graphs are a very low level way of representing a multi-agent system. So it'd be nice to have some higher level language, something which more resembles a programming language. And so that's what we do in what are called reactive module games. We use a high level specification language for our agents, a model specification language, a language which allows us to describe our agents in a high level way. Technically, it's a guarded command language. In AI terms, we'd call it a rule-based language. It was introduced 20 years ago, and it's very well established. It has a very nice, clean, elegant semantics, which is basically what's particularly attractive for us. So here is an example of an agent specified in reactive modules. So in reactive modules, each module is an agent. I regret that they decided not to call them agents, but there we are. And this is what they look like. And basically, as I say, it's a guarded command language, but you could think of it as a rule-based language. And there are two sets of rules in each agent. There are what are called initialization rules and update rules. And the initialization rules govern how the agent may initialize itself at the start when it begins computation. And basically the way it works is, in our formalism, is that we give a bunch of these rules, but we don't specify which of them will be chosen. And the agent can just choose any of those rules to initialize its variables. So if we look at this syntax here, this funny symbol on the left-hand side is just a separator symbol, so ignore it. The open and closed square brackets. The business part is on the right-hand side of that. It's a rule which has got a condition part, and this particular condition just means true, right? So it's something which is always true. And then on the right-hand side of the arrow symbol, we've got the action part, and the action part is just going to specify how the agent controls its own variables. And in this case, what it says is, I'm going to set x to be true, and this following rule, it says it sets its x to be false. So you'll notice at the top there, we specify the variables that each agent controls. So there are two initialization rules. One of them which specifies that x becomes true, one which specifies that x will become false, and we're not dictating which of those is chosen. So the program just chooses initialization, just chooses one of those rules to execute. Then we've got our update rules, and what this first update, and on subsequent rounds after the agent is initialized, the initialization rules are only used once when it starts executing. Subsequently, what we do is we use the update rules, and it's the same idea. We've got a bunch of rules, and each of those rules has got a condition. So the condition on this first rule is that x is true. The condition on the second rule is that x is false. And what it will do is it will look to see which of its rules has a condition which is currently satisfied, and it will choose one of those to execute. And again, there could be more than one of those rules, in which case it's just allowed to choose. And a strategy for an agent is just a rule which defines how it makes choices. So a bit formally then, an arena just consists of a set of agents, 1 through to n. So big N here is a set of agents. Phi is the set of Boolean variables. This is the set of Boolean variables in the system. And then for each agent, we've got a module, and a module consists of the variables that agent controls, its initialization rules, and its update rules, exactly the way that we described previously. What we haven't yet got is the preferences of agents. So how do we specify the preferences of agents? What we do is we give each agent a goal. And we give each agent a goal which is specified as a formula of temporal logic. And we could use any kind of temporal logic. We tend to use LTL or CTL. And in most of the remainder of this talk, I'm going to focus on LTL, which I've already introduced to you. So these gamma sub i's here, these are the goals of, this is the goal of agent I. And the idea is that the agent I then, its goal is to get gamma sub I achieved. When all of these agents have chosen a strategy, which the strategy is going to dictate how they make choices, how they choose their rules over time, when all of those strategies have been chosen and we run all of these agents against each other using those strategies, what we generate is a run, a computation, right? A linear path, a path through the space of possible computations that we saw earlier. And that path is either going to make gamma sub I true or false. And the idea is that by specifying this goal gamma sub I, that basically the agent wants to make I true. So that's what its preferences are. So let's have a look at some decision problems. So remember E-Nash, A-Nash problems that we talked about earlier. So the E-Nash is, given a game G in an LTL formula phi, does that property phi hold on some Nash equilibrium of the game? Right? Does it hold on some Nash equilibrium of the game? The A-Nash, and when I say hold on some Nash equilibrium of the game, a Nash equilibrium is a collection of choices which is rational in the sense that no agent has any incentive to do anything else. Okay, so a collection of strategies then is a collection of strategies is a Nash equilibrium if no agent has any incentive to do anything else, assuming the others stick with their part of the strategy profile. A collection of choices is going to induce a run, a computation, and that's going to either make phi true or false. So in the E-Nash problem, we're saying, does phi hold on some Nash equilibrium of G? More precisely, is there some Nash equilibrium computation of G such that if you executed those strategies, then the computation which resulted would satisfy phi? And the A-Nash, it just asks the obvious variation of this, does phi hold on all Nash equilibrium computations of the system? Then we've got a more general question, the equilibrium checking problem. We've got a game G and we've got a strategy profile. How do we write down a strategy profile? What we use is finite state machines with output transducers, or Moore machines they're called. Technically, you don't need to worry about that. Just think about basically the strategies are just a computer program which selects one of the rules for our agent. And in equilibrium checking, we're just asking whether a particular combination of strategies, what's called a strategy profile, forms a Nash equilibrium of the system. Okay, so the first results that we get are the E-Nash and the A-Nash problems for LTL games where the goals are represented in LTL or in they are 2x time complete, whereas the equilibrium checking problem is what's called p-space complete. So 2x time is a very negative result. P-space completeness is still a negative result, but slightly better. And what's interesting about the second one, the p-space completeness result, is that we've got a game theoretic question asking whether a bunch of strategies forms a Nash equilibrium, and actually it has the same complexity as the regular model checking problem, the problem that I described to you earlier. For CTL, however, the equilibrium checking problem blows up. It gets considerably harder. Let's just see a tiny little example. This is a simple example. Here we've got two players, and player one controls P, and its rules say that it can do whatever it wants to P. It can set P to be true or false. That's what its rules say. Player two controls Q. Player one's goal is it wants P and Q to take the same value infinitely often. Player two wants them to be different infinitely often. Now, it's easy to see that they can both get their goal achieved, and I've just written down some finite state machine strategies to do that. Player one just fixes P to be true, and it just every single cycle it just always chooses that P will be true, while player two alternates with the value of Q. It just flips between those two values infinitely often. And what you get is a state sequence where P and Q are true, and then Q is false and P is true, and then they're both true again, and so on. So you get they're both the same infinitely often, and they're both different infinitely often. So with those strategies that I've drawn there, both players will get their goal achieved, and when both when all the players get their goal achieved, it's a Nash equilibrium. Okay, we've implemented this framework, and you can use this framework to simulate, for example, multi-agent planning systems and a whole bunch of other nice nice frameworks. We've implemented it through our DPhil student Mohammed Najib has implemented it in the Eve system. You can follow this link, eve.cs.ox.ac.uk, and you can play with it. Because it's dealing with problems which are computationally very complex, it has to use some quite heavy algorithmic techniques, and it uses a bunch of translations between various different types of games and various different types of automata. So that's the equilibrium verification environment system. So the punchline is this: we have the framework that I've just described to you. We have implemented, and I say you can experiment, and you can check the eNash and aNash problems, and you can check whether equilibria exist, whether particular strategies are equilibria, and so on. Okay, let me move on just for the last few minutes. I just want to talk about a different approach, and the different approach is agent-based modeling. So the example that I used at the beginning was of flash crashes in global marketplaces, and this is a very real problem, and we're genuinely very interested to that. The truth is the techniques that I've described so far are not going to scale to that, right? We're not going to scale to millions of agents. It just isn't. When you're faced with a system like that, and you want to understand its equilibrium properties and when it can fall out of equilibrium, its disequilibrium properties, you need different approaches. And the approach that we use is agent-based modeling. And agent-based modeling is an old idea, but an idea which has really come to fruition in the last few years, where you model a system down at the level of individual decision makers. So in agent-based modeling for flash crashes, what you do is you model down at the level of individual traders. There are a number of issues. It's an old idea, and there are a number of standard problems in agent-based modeling. First is getting meaningful simulations. It's very easy to build an agent-based model, but most of the behaviors you see in it when you start tend to be nonsense. So actually, it's a challenge just to get realistic behaviors. Secondly, the related problem of magic numbers. When you start tuning your model so that you get some behavior in your simulated system that resembles real world behavior, you've got somewhat arbitrary parameters in there. So dealing with those is a real challenge. The calibration problem, knowing when a dollar in the model corresponds to a dollar in the real world. And finally, qualitative versus quantitative interpretations. If your simulation, and you need to run these as Monte Carlo simulations for a wide range of parameter settings with lots of random numbers generated along the way, to what extent can you quantitatively trust what's coming back? If your simulation says in 20% of my simulations we got a flash crash, does that really mean in 20%? What does that number mean in the real world? Can you take it as that there is a 20% chance of a flash crash occurring, for example? So our DPhil student, James Paulin, he specifically looked at flash crashes, and he was interested in the effects of what are called leverage and crowding. Leverage is basically where you borrow lots of money in order to be able to buy things. Crowding is where lots of different investors buy into a particular stock or a particular share. And James did agent-based modeling with very, very large numbers of agents, and exploring particularly issues of calibration and so on, and found some quite remarkable results. So, for example, the standard assumption is that crowding is dangerous. If everybody invests in a stock and that stock becomes distressed, then that propagates the distress throughout the market. So crowding can be a bad thing, is the usual assumption. But James found that paradoxically it can actually be beneficial to system stability under certain particular cases. And also found a number of other results. For example, the speed of flash crash propagation depends on leverage, capital, and network topology. Oh, so I should have said, actually, agent-based modeling is important here because you want to understand the actual structure of the system in terms of the decision makers in it. So just to wrap up then, I mean, what I'm interested in is multi-agent system dynamics, and what I've approached to describe to you two very different approaches to understanding multi-agent system dynamics. The first is very mathematical, very analytical, and it's based on the idea of treating bad behaviors in a system as a bug and then applying techniques that have been developed to understanding and finding bugs, but adapting those to make assumptions about the rational behavior of agents in the system. And we've made some progress on systems that can automatically analyze these game theoretic behaviors of a system. The second approach, agent-based modeling, which I didn't talk about too much, is based on the idea of directly simulating a system and running it for a large number of possible behaviors. My dream ultimately is to try to bring those two approaches together. What I would like to be able to do, and we're just very fortunate to have a large project funded for the next 5 years, what we want to try to do is to bring together agent-based modeling and the rational verification approaches. What I want to do is build a model like James Paulin's model and then query it in the same way that we do in model checking and in rational verification. For that, though, I have to say that it raises all sorts of questions, for example, about the assumption of rational behavior by the agents in the system, how much those agents can see and know, and most fundamentally, it raises problems of scale. So now we're looking into the future to see what the techniques are that we might use to achieve that goal. So once I'm done with my presentation, once again, let me thank you for giving me the opportunity to speak. Apologies for not being able to join you today. There's nothing I could do about that, unfortunately, but thank you for the opportunity to speak. And I hope I hope you enjoyed my presentation, and I hope to meet you all very, very soon at this event in the future. Thank you.